We're going to start by talking about maxima, and minima, which is the plural of maximum and minimum, and increasing and decreasing intervals. Okay, so we're going to talk about maxes and mins first. So basically, what we would call a relative max or a relative min. Those can also be called local max or local min, so relative or local. That refers to a point on the graph that is higher or lower than the points to the left and to the right of it. So for example, this is a local or relative max. And these here would be local mins. So notice it looks like the bottom of a little valley there or a hole or something like that. The max is like the top of the mountain. We also have absolute maxes and mins. And the absolute max would refer to the largest y value in a function. The local min would refer to the smallest y value in a function. On this graph right here, you guys see either one of those things? That one, yes. This is the absolute minimum. Because there is no point on the graph that is lower than that point. What do you guys think about absolute max? So, infinity. Okay. So, what you're noticing is that this graph goes up for forever. So the only reason we don't say the max is infinity is because infinity is not a number technically. So we would say there is no absolute max for this because it keeps getting bigger. So no absolute max. The way that we say the absolute minimum is we want to say the absolute min is -3 at x equals -4. So we say the y coordinate, because we're talking about min and max, we're talking about y coordinates. And then the x value tells us where it is. So using that same convention, what would we say for our relative or local max? What would we write? So,
2 at x equals 1.
Yes, 2 at x equals 1, exactly. For the relative min, we have 2 of them, and one of them is the absolute min. So what I usually do is just like have a little arrow pointing to it to say like that's one of them, and then list the other one. But it's also fine to list them twice. And you can use the little at abbreviation like I'm doing, or you can write the word at. It doesn't matter.
We can do the at.
Yep. You need to acknowledge that they both are relative mins, whether it's pointing to it with an arrow or writing it. Like.
So are all the relative mins just negative factors?
What?
So all the relative minimum values, are they all the negative y values?
No, they are the lowest points. They are like this point and that point there. The points at the bottom of the curve there. Like the bottom of a parabola. Okay, now, there's actually a little bit of ambiguity. So in terms of absolute mins and absolute maxes. So there's a little bit of a debate. So there's one argument that says, okay, well, all absolute maxes and mins are a type of relative max or min. And that's very similar to the example that we just saw, right? This one was the absolute minimum, but it's also a relative minimum. If it's the lowest point in the graph, of course it's going to be lower than the points very close to it. Or another analogy would be like, if I'm absolutely the tallest person in the world, I'm taller than every other human, then if I go into a room full of people, I'm also guaranteed to be relatively the tallest person there. Like, I'll be the tallest person in the room because I'm taller than everyone else in the world, right? So that's one argument. But there's another argument, and actually this one is more common, that says we have relative maxes and mins, and we have absolute maxes and mins. And sometimes there's overlap, like in the example we just saw, but also sometimes they're different. And actually more people think this second one because of examples like this. So on some kind of line segment graph, we would for sure say that this is the absolute min. There's no argument about that. What the argument is about is it a relative min? It's lower than the points to the left of it, but there are no points to the right of it. And so we can't really compare both sides of that point to say for sure if it's a relative min, because the relative min kind of needs to be lower than the points on either side. And maybe, we don't know this, but maybe this graph is part of a larger graph where the function keeps going down, and we've just cut it off and said, hey, look at the red part, ignore the blue part. And so it would be wrong to say that this is a relative min if it's part of a graph that's on the way down. But if we're just looking at the interval that we were being told about, it would not be wrong to say it's an absolute min. So this debate kind of comes down to what you think about the endpoints. All this to say, you're going to find some cases where you're like, wait, should I call that a max or a min? And it might be that it falls into this sort of ambiguity of, well, we don't know. Long story short, I'm not going to ask you a question that is going to force you to pick a side, and I'm going to penalize you. I'm going to penalize you for picking the wrong side. I kind of fall into this category, but that's the minority opinion. So we'll circle back to this on the problem on the back of this paper and talk about how the question would be phrased to kind of avoid that. But when we look here at number 3, for example, the debate would be about this point right there. Like, would we say that that is a local minimum? And the answer is maybe. Some people would, some people wouldn't. Because it's definitely lower than the points to the left of it, but there's no points that are immediately to the right. The graph like jumps up here and is doing something else. So it's kind of ambiguous if we would say if that's a min or a max. And that's the answer I'm saying is I'm never going to ask you about that right there. So what I would say for this one is, for number 3, here's some things that are not up for debate. There is no absolute max. Because this highest point on the graph is an open circle. And so that graph never reaches 7, but what's the highest value it does reach? 6.9, 6.99, 6.9 repeating. Well, 6.9 repeating actually equals 7. So it doesn't equal that. So there's no absolute max because there's no number that we can give.
Does 0.9 repeating equal 1?
0.9 repeating does equal 1. And there's also no absolute min because this graph keeps going for forever. Something else that's not up for debate. This is a relative max. It's got points to the left and to the right that are lower than it, so we would say for sure that is a relative max. How would we write that as a relative max? What would we say? 5 at
5 at -3.
at x equals. Okay, the point that would be up for debate is whether or not this graph has a relative min. Like I said, I'm not going to ask you about that point. You might think to yourself, yeah, it's definitely a relative min, in which case you would fall into this category. Or you might say, no, I don't think so, in which case you would fall into the other category. So again, I'm not going to ask you about that. Okay. In general, so this is true of maxes and mins, and it's also going to be true of increasing and decreasing. We are always giving x values to say where something is happening, and the y values describe what is happening. And this is always true in functions. So when I say, for number 3, what is the relative max? We say it's 5. Where is it? Well, it's at x equals -3. Yeah, and that's always the case. And so when we say, okay, where, I might say where is the function increasing? So where means my answer is going to be x values. When I talk about the function, what is a way to abbreviate the function? F of x. And what's another way to write f of x? Y. Okay, so when we say where is the function increasing, we are saying where is f of x increasing, which is the same as saying where is y increasing. So where are the y values going up? And we always look at that from left to right. So my question of where are the y values going up is going to be answered by x values. So on this first one here, we would say the function is decreasing right there and right there. So as we read from left to right, the y values are going down. It's angled like negative slope. We would write negative infinity to -4 union 1 to 3. For number 1.
When you're actually at -4.
Okay. Yeah, so and now we stumble into our second mathematical debate of the day and the year. They happen on the same day. Of whether to use brackets or parentheses. We actually can use brackets for this if we want, except on infinity. And there's an argument for both. The argument for using parentheses is like, well, at a single point, we're not increasing or decreasing. But the other argument is, well, we're decreasing through that point. I would say it's always safer to use parentheses. I'm always going to use parentheses. I prefer it. Parentheses are always right. With brackets, you have to be careful of which ones you use where. Oops, that's a bracket. So again, brackets and parentheses, I'm not going to penalize you for that. Just don't put brackets on infinity. Don't put brackets on an open circle. Don't put brackets on an asymptote. Is that your question?
Yeah, it's like it's still like part of it.
Yeah. So parentheses are always going to be right. So I keep parentheses. Okay, increasing would then be here to here, and here to here. So -4, 1, union 3 to infinity. Again, I'm always going to use parentheses for increasing and decreasing. Okay, so number 3, where would we say number 3 is increasing? Mike?
Negative infinity to 3. You're -3.
Negative infinity to -3. Anywhere else? Or is that it? That's it. Okay. And then where are we decreasing? Yeah. Yes. So for that break in the graph, we would say it is decreasing until that point, and then it stops because there's a jump in the graph. So it's not like continuously decreasing, but also jumping from this lower value to this higher y value doesn't count as increasing either. It's just a jump in the graph. And so we would just say it's decreasing until -1, and then it stops for a second and then resumes. Yeah, that's a great question. The answer is I'm not exactly sure, because if I saw a bracket on -1 and then saw parentheses on the same number, that to me is like contradictory information. So there's probably a right answer to your question, but I don't know, which is why I always use parentheses.
Could you explain why the equation would be negative infinity from -3?
Because we are starting here at negative infinity and we're going up, 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 up until this maximum value. We read from left to right. Okay. Okay. All right, you guys do number 4.
I thought that was.
Okay. Number 4, do we have an absolute max? No, we don't. This graph is going up for forever. Do we have an absolute minute? Yes. What is it?
0
At x equals?
-4 and -4.
Yeah. Okay. So if we want to be fancy, we could say at x equals ±4. We could also say at x equals 4 and -4. We can list it. There's a lot of different ways we can list it. So x equals 4, x equals -4. A lot. So either way. Okay. Do we have a relative max? Like
4 at x equals 0.
4 at x equals 0. Yes. There's our relative max. Another way to define a relative max or a relative min is a change from increasing to decreasing. That's another way to identify one. Or a relative min would be a change from decreasing to increasing. Something you're going to do a lot in calculus. Okay, relative mins. Do we have them? Saba?
0 at x equals 4 and 0 at x equals 8.
Nice. So if you want to just draw an arrow pointing to that, that's fine. If you want to list them again, that's also fine. I'm more concerned with you showing me that you know that those are both absolute and relative. Okay, where are we increasing? And where are we decreasing? Notice the relationship between the increasing and decreasing and the maxes and mins based on the other way to define it. Like, if if we have a max, if we have a min at 0, we know that we're going to be decreasing before that and increasing afterwards. And those numbers all agree with each other, and vice versa for the max. Questions on that? All right, let's go to the next page here. So here's an example AP calculus question.
I got that.
Yeah, so on the AP exam, they'll have a bunch of free response questions like this. Most of them will have to do with just calculus, but I think there's about one every year that's just from pre-calculus. On the review guide for the trig proofs test, we had a couple of AP questions that were on there. I don't know if you remember that, but this is an example of a question that is just from pre-calculus. There might also be some parts like 7 and 8 that were cut off, but that has to do more with calculus. But anyways, this is kind of the idea. So one thing based on what we were talking about earlier that I want to talk about is number 2. So at what values of t is there a local minimum? What values of t is there a local maximum? Okay, so remember we said, or I said, that there was a debate between whether or not these points should count, right? Like this is for sure the absolute minimum. Do you guys agree? And maybe we could say that point is a minimum too. Or maybe we would say it's not a minimum, depending on which side of the debate you fall on. Because, and notice there's nothing, it doesn't ask it like that on this question. So back in 2010, what they would have just done is they would have accepted this as a local min, or they would have been fine if you didn't list it. The way that they do it now to kind of avoid this whole debate is they say on the interval 0 to 8 in parentheses. So when we say 0 to 8 in parentheses, that means don't look at these endpoints right there. So that's how they're going to phrase it to avoid that. And if I'm going to ask you about it, that's how I'm going to phrase it. Okay, so let's answer this question. At what values of t is there a local min or max? What would you guys say? So, okay, local max of 1,200 at t equals 2. Okay, does that answer the question they asked? This is a little tricky. What did they ask? It would just be 2. Yes. Because it's asking at what value of t is there a local max. So AP exam's a little tricky sometimes. But yes, that's the local max right there. We would say local max. Same thing as relative max. You can use either word. At t equals 2, you would say no local min or minimum. Okay. Let's look at number 3. Find the average rate of change of R of t from 0 to 8. When you guys see that word rate of change, what does that make you think of? Slope. Yes. That's exactly what it should make you think of. Rate of change is slope. So it's asking the average slope from 0 to 8. Notice, from 0 to 8, we've got a lot of different slopes. We have a positive slope here. We have a negative slope. We have a 0 slope. We have another negative slope. Any ideas on how we're going to find the average slope from 0 to 8? Here's what we're going to do. We're going to take this point where it starts and this point where it ends, and we're going to find the slope between those 2 points. And that's going to be our average slope. Because overall, the number of people per hour is decreasing as time goes on. And that's how we find the average slope. We just find the slope between the first point and the last point. So maybe easier than it seems. What's the slope formula? Rise and run. How do we do that? Why?
You find 2 points that you plot on the graph, and then you take whatever the rise is and put it up there. Or 2 points are on the line. You know what I'm trying to say? I can't say it.
Kira, what you got? That'll do it. Yeah. We can also do y2 minus y1 over x2 minus x1. Yeah.
I don't know what that is.
Or I'm seeing, okay, yeah, it's going down 1,000 to the right 8. So minus 1,000 over 8. Or I do 1,000 minus 0 over 0 minus 8. We need to simplify that number. 125. The way I do that division in my head, by the way, is I did 1,000 divided by 4, which is 250. That's a little bit easier to do. It's like 100 divided by 4. And then 250 divided by 2. I don't know 1,000 divided by 8 off the top of my head, but I know 1,000 divided by 4. So we would say negative 125 people per hour. Okay. You guys do numbers 1, 4, and 5, and we'll come back to number 6. All right. Okay, this first part of the equation, what is our equation for that part of RT? Set slope was 100 already. Y-intercept. 1,000. And that's from 0 to 2. Okay, the next part there, what's the slope of that? Slope? Negative 400. And then y-intercept, 1,800. 2,000. Yeah, so I would see it would go up to 1,600. It's going up 400, right? It would go up another 400 to 2,000. That's probably how I would do it. I would just trace it up there.
Yeah. Also,
But remember also we could do this point shifted like right to up 1,200. That would also. Okay, the next part, the flat part there. 400. Yep. And then the last part. Negative 200 x plus 1,600. All right. Okay, again, remember that for 6, 4, and 2, we need one equal sign in our inequalities. but not to an equal sign. So if I do less than 6 here, I need to do greater than or equal to 6 here. If I do greater than 6 there, that needs to be less than or equal to. Okay, where is this function increasing? 0 to 2, decreasing. 4, 6 to 8, and then constant 4 to 6. Yeah. So constant we didn't talk about. What constant is the flat slope, no change, not increasing or decreasing. Okay. What is R of 0? 1,000. R of 0 is 1,000. What is R of 3? 800. What is T when R equals 200? 7. Okay. Then once we get into these, I say R of 1.5. That's not as easy to do. Like, what is that Y value right there? Yeah, I mean, maybe 1150, maybe. That actually is what it is. But the way that we know for sure is we have to take 1.5 and we need to plug it in for x. Which equation will we plug it into? Yeah, we're going to plug it into that one because 1.5 is on that interval right there. So this is just like those homework questions. So 100 times 1.5 is 150, plus 1,000 is 1,150. So then the next one we do R of 6.75. That's like there. We're going to have to take 6.75 and plug it into which one? Yeah, we're going to have to plug that into this one. So 200, negative 200 times 6.75 plus 1,600. So 2 times 6.75 would be 13.5. So this would be negative 1350. Plus 1,600, 250. So then now we need to find T when R of T is 625. So 625 is happening right there on this region. So our answer is going to be 3 point something. How do we do that one? Set it equal to what? Set what equal to 625? Yeah. So we're seeing that's in this region. We're given the y coordinate this time. We have to set this equal to negative 400x plus 2,000. So I've got to subtract 2,000 from both sides. Get negative 1375 equals 400x, negative 400x. I'm dividing this by negative 400. If I don't have a calculator, which we wouldn't for this, what I would do is just do long division with 4. I would do 1375 divided by 4. And then move the decimal place. Yeah. So 4 goes into 13 3 times. 4 goes into 17 4 times. 4 goes into 15 3 times. And then we're left over with a remainder of 3. You can either add decimal places here and drop the 0 and keep going. Or if your remainder is 3, that means it's 343 and 3/4. It's 3 over 4. Or 343.75. So then we would move that decimal over. 3.4375 would be our answer. Mike.
So you said we won't have a calculator on the test?
Correct. There's only one unit we use calculators, and it's come and gone. It's an easy number. Okay, let's go to the next page. Like I said, today's gonna be notes heavy. The next class will not be. Okay. So we're talking about continuity in graphs. We're going to talk about 3 types of discontinuity. This part's going to go a little faster. What does it mean for a function to be continuous? Goes on. Mikey?
There's no beginning or ending point.
No beginning or ending point? No, that's not what it means. It's a good guess, though. Hey, you got something? Continuous. What does continuous mean in a graph?
The graph ends with arrows.
No. Okay, so you're confusing continuous with infinite. These are actually different things. Continuous in English is a lot of times synonymous with infinite, but in math they are not synonymous. Brandon's got it.
Is the line that does not break and still has the whole piece together.
Okay.
Inside.
Okay. So one piece, no breaks, just like math class today. No breaks. What kind of breaks could you imagine in a graph? Holes, yep. Asymptotes, yep.
Gaps.
Gaps of any kind, yep. Yes. Okay. Yes. So this is what continuous means. Continuous is very frequently confused with infinite because continuous does kind of sound like something's going on forever. That's actually not what it means. It just means all one piece. So like a line segment is continuous. If that's our graph, that is a continuous graph because it's all one piece. From beginning to end, there's no break. Graphs can be infinite and continuous. They can be infinite but not continuous. They can be continuous but not infinite. They can be neither. Okay, so there are 3 types of discontinuity. One of them is called an infinite discontinuity, which is also known as a vertical asymptote. That is type 1. We've called them vertical asymptotes all year. They're also called infinite discontinuities. You'll see what we're talking about right now is really, really related to other topics that we talked about. So anytime that we would divide by 0 in a graph, so now we're thinking domain, we're thinking, that's standard 31, we're thinking standard 4, which is graphing rational functions. We can make a connection to our parent function, 1 over x shifted to the right, 2. All these things are going together here. But focusing on just the discontinuity part of this graph, we would say, we have an infinite discontinuity at x equals 2. We could also say we have a vertical asymptote at x equals 2, which is saying the same thing. So you can call it infinite discontinuity, you can call it a vertical asymptote, either one's totally fine. Notice we're also, again, we're using the x values to say where this is happening. Okay, so horizontal asymptotes are actually separate from continuous or not. Because horizontal asymptote, we could have a horizontal asymptote, but it function be continuous. In this case, it does kind of split the function there, but that's only because of the vertical asymptote. Yeah, so we're actually not going to list it when we're talking about discontinuity. Good question. Sure. Okay, so again, and we've talked about this all year, right? We're not allowed to divide by 0. If we're left with something on the bottom that would make us divide by 0, that's going to create a vertical asymptote in the graph. When we have a vertical asymptote, that's the same thing as an infinite discontinuity. What is the discontinuity in letter B, and where is it? It's at 4. And what is it? Vertical asymptote. Or we could say infinite discontinuity. Yeah. Infinite because this is going like down for forever, this is going up for forever. These lines are approaching infinity. And they're very far apart. What could be the equation of this function right here? What's that? Yeah, it could be 1 over x minus 4. Yeah. So we've talked about this a number of times this year. We also, it's been a while since we've talked about these, but we have removable discontinuities, which are also known as holes in the graph. So letter B, here we have a hole. Looks like it's at it. I'm just going to say it's 1. You could call it a hole. We could call it a removable discontinuity. One of those has way fewer letters than the other one, so I might go with that one more now. Discontinuities are very obvious when you look at a graph. They're a little bit less obvious with the equation. So right here, I would say if I saw that on the bottom, I would be thinking vertical asymptote at x equals -3. But what do we have to do on the top? Factor. This factors into x plus 3, x minus 3. So when the x plus 3's cancel out, that's why it's called a removable discontinuity. Because it cancels out. There's now nothing left on the bottom. But canceling this factor out creates a hole in the graph. Okay. Again, it's called removable because there's no longer anything on the bottom of this that's making it equal 0. It canceled out. But we know that anytime factors cancel out in a function, that creates a hole in the graph. You can also relate this to our composition of functions. Remember, we canceled out that domain, or sorry, that denominator from the top and bottom. We still had to include that in our domain restrictions. The last type of discontinuity is called a jump discontinuity. Again, very obvious in the graph when it happens. If we look and we see, oh, these graphs do not connect. No, -3. It's a number that makes it equal 0.
Oh.
So a jump discontinuity we can see is when the y values jump, right? We have two pieces of a graph that don't intersect each other. This can only happen in a piecewise function. So here we would say we have a jump discontinuity at x equals 2. Again, visually it's very obvious. when we just have the equation, how would I know if the two pieces of this graph met each other? How would I know if they were going to intersect? How? Yeah, put -1 in for x for which one? For both, exactly. We plug in -1 for x in both of these. That's going to tell us where our graph hits the boundary line. Okay. So we plug in -1, we see those two things do not equal. That tells us that if we were going to graph this, you know, for x greater than -1, we've got our 2x plus 1 graph. That'd be going like that. It would intersect here. We could also graph this and figure it out. Our x minus 4 graph would look like that. That's a jump discontinuity based on what we got right here. Okay. It is possible to have multiple types of discontinuity in a graph. So we're going to look at 3 and 4. Okay, so in number 3 here, we would want to factor the top and bottom. When we factor, we see that there is a factor that cancels out. What's that going to create in the graph? A hole. So there is a hole at x equals -1. But then also we're left with something in the denominator, x minus 1, which is going to create what kind of discontinuity? An asymptote, or an infinite discontinuity. So we have a vertical asymptote at x equals 1. So we have both. For number 4, when we plug in -2 for this and -2 for this, that's going to create a jump. We're going to see that the numbers aren't equal. When we plug in 2 to both of these, that's another jump. But also, that part of the function right there is going to give us what type of discontinuity? Asymptote, yeah. At x equals 3. So we have a piecewise where we have 2 jumps and vertical asymptote. So they can be combined. Last thing I want to get on here is end behavior of polynomials. This is standard 1. This is the second day of school. So odd polynomials, odd degree, like x cubed, looks like that. Remember the way that we write that is the limit of f of x as x approaches -infinity. It's -infinity. The limit as x approaches +infinity of f of x is positive. That's our way of writing it. Negative odd would look like this. It would be the reverse. So as x goes to -infinity, the graph goes to +infinity. As x goes to +infinity, y goes to -infinity. Our even degrees would look like this. Positive, negative. here's our limit notation. Whew. Okay, maybe we will